and I put as I wrote to you, I put the PDF file up on my website. I'll give you the link. Give the link again at the end of the week for the PDF for this talk. And let's start. So it's a 5-lecture series, and don't get too upset if you can't do these challenges so easily, because some of them range from easy to major parts of a course. And I don't really sort of tell you which one they are. See, so you have to sort of dig in a little bit. And today's no exception. Now, in the first talk, we discussed what's called propositional calculus. And there we just had, if you remember, statement letters, and A1, A2, and so forth. And we had our 5 connectives, not, and, or, if, then, and if and only if. Now, in this talk, we want to talk about a far richer framework called predicate calculus. And we'll approach the predicate calculus in small bite-sized stages, because swallowing the whole thing in one talk, if you haven't seen it, or even if you have seen it maybe only once before or something, is actually pretty imposing. So we'll do it in stages, and actually these stages are themselves already subjects of serious interest in and of themselves, particularly in computer science applications. So now propositional calculus is nowhere near powerful enough to support what's really going on in mathematical thinking. Mathematical thinking, you know, has a lot of variables, you know, x and y. You've seen that, x and y, okay. And of course, things like for all and exists. So we know that propositional calculus is too puny to really handle the logic underlying mathematical thinking generally. But predicate calculus is powerful enough in various senses. Predicate calculus is the right framework. Now, I'm going to have you eat. Let me put it this way: I'll be serving a lot of vegetables in this talk, and then at the end, though, towards the end, we're going to have some special fun. So this is to make sure that you just, you know, you don't want to leave early. I have been told pretty much that I'm going to have to be out of here. Normally, I want to, you know, sort of wind up at, finish up at 11:20, but at 11:30, there's going to be more people in here doing something quite different. So, so I won't be able to stay forever, even if I'd like to, because we're going to be having so much fun, you know. We want to go on, you know, maybe till midnight, but we won't be able to do that. All right, so just wait till the end of the talk, or towards the end of the talk. All right, so now in this talk, we're going to scrap the sentential letters A1, A2, and so forth, but we are going to keep the 5 connectives, not, and, or, if, then, and if and only if. That we're going to keep very much. But now we're going to introduce variables, v1, v2, dot, dot, dot. Now, v1, v2, dot, dot, dot are the official variables. When you actually, you know, use variables in mathematics, you usually like to write x, y, z, or whatever. You don't like to have a lot of subscripts. But sometimes, of course, you have to. But you sort of like to avoid it. It's ugly. So, so in this very primitive setup, so think of this as warm-up. This is pre-vegetables. These are not even vegetables. This one is a little bit earlier than vegetables. Yes, this is maybe a glass of water. This is what this is. Here we go. Okay, so the variable equations just take the form vi equals vj, or if you like, x equals y. And the variable formulas are built up from the variable equations using our 5 logical. Using the 5, GIVE is not 5. GIVE, 5 logical connectives. All right, example of variable formula, V3 equals V3, or not V3 equals V4, or V3 equals V4. Anyways, the last one, V2 equals V7 and V9 equals V1, if and only if not V8 equals V2. So you get the idea. And everybody likes to write VI not equal to VJ instead of not VI equals VJ. In other words, everybody likes to write X not equal to Y instead of not X equals Y, right? Okay? Very, very simple little setup. Okay. So now what is variable formula logic? Actually, this is so primitive, nobody really wants to talk about it too much except me in this lecture series. So I had to make up a name, variable formula logic. Okay, because it's so puny. All right? In variable formula logic, we only have these variable formulas, which are, as I wrote, sort of combinations. They use the variables, equations between variables, and the connectives. That's all, if you just remember what we had here. On the second to last line, that kind of thing. Okay? So these are the variable formulas. Now to interpret the variable formulas, so in logic you have symbolic representations, formulas, so to speak. Logical formulas, and then you want to interpret them. You want to say what they mean, and then you also want to be worried about whether you can prove them in some calculus, logical calculus or whatever, right? This is the pattern throughout the talk. So we designate a non-empty domain D. So these variables, what do they stand for? Well, maybe in grade school they stood for positive integers. That was the only kind of things that you could understand in second grade. Counting numbers, 1, 2, 3, 4. Later, variables might range over integers as you got more advanced, right? Because you have 0 and the negative integers. So, anyways, you pick a non-empty set D, and the variable formulas will be true or false in D, depending upon which objects from D are assigned to which variables. Now, I put equals there because we are assuming that we have equals. Otherwise, we couldn't do anything at all here. We just have variables lying around. We got to say, in order to say something, we have to say that two variables are equal. Okay, so and now if we're not talking about assignments. So, for example, x equals y is true if x is assigned 3 and y is assigned 3, and x equals y is false if x is assigned 3 and y is assigned 4. That's the kind of thing I mean. So, but now if we don't mention an assignment, we have the definition, a variable formula is said to be true in D equals if and only if it is true under all assignments. That's the convention. If I don't mention any particular assignment, then being true means it has to be true in all assignments. This is a convention almost all throughout the entire logic subject, this kind of convention. Okay? All right. Now here's some examples. Among our examples were these three. V3 equals V3, V3 not equal to V4, or V3 equals V4. V3 equals V4 implies V4 equals V3. Notice that these three are very special. They're true in D less than no matter what D assignment you use, right? I don't care what you assign to these variables as long as the same variable gets assigned the same thing. That's very important. That's also all through logic. Same variable gets assigned the same thing. That's an important theme. Okay? No matter what assignments I make, all three of these things are going to come out true, correct? No matter what assignments I make. And that actually doesn't even make any difference what my domain is. It could be integers. It could be the set of people in this room. That's a perfectly legitimate domain also. Okay? It's smaller than the number of integers. There are finitely many people in this room, actually. But basically, it doesn't make any difference what D is. D is required to be, by the way, non-empty. Another theme throughout all of logic. A domain must be non-empty. There's reasons for this. You might say, why do you do that? Well, there are reasons for this. I could probably spend a lot of time talking about the reasons, but let's not talk about that. That's just a convention. Okay, so we have here, So that means that there are some D assignments. See, if D was empty, there wouldn't even be any D assignments. That's another problem, right? So we like to have D non-empty. So it doesn't make any difference what D is. It doesn't make any difference what the assignment is. These three come out just fine, right? Okay. All right. I hope you're with me now. Okay, so fine. All right. Repeating myself there. Such an equational formula, I'm sorry, the word equational formula is a remnant of the past. What I mean is, such a variable formula is said to be valid, okay? I was playing around with different terminology. Such a variable formula is said to be valid if it's true in all D comma equals, which means it's true in all D comma equals under any assignment. Okay, now I have a theorem here for you. If a variable formula is true, this is some nice vegetables. Say this is some corn, okay? If a variable formula is true in the integers, then it is valid. In other words, if it's true in the integers, it's true in any domain, non-empty domain. And by the way, this claim is false if I were to use a finite set instead of Z. If I was to use a finite set, a finite D, then this claim would be false, okay? And your challenge is to prove this. That doesn't mean right now. It means when you pore over the PDFs and you feel like you have the time to think about it, you can try to do this, okay? Now, I'm warning you, these things range from easy to major parts of a course. And I'm not telling you which one this is, okay? I can tell you that it's not at either endpoint. It's in the middle. Okay, but that doesn't tell you, but it could be, that's still a big range. All right. Now, can all valid formulas be proved? In other words, is there a sense in which I can prove all valid formulas? You know, by the way, a constant theme throughout logic is you want to be able to prove all the things that are, in some sense, correct. You want to be able to prove them all. This is a common theme through logic. And by the way, we will run into situations, not in this first two lectures, but later, where you can't do that. You're never going to be able to prove all the things that are correct. And in fact, it's a theorem that you can't do that. That comes up in, there's a lecture here called Gödel's Blessing and Gödel's Curse. Well, that's the curse, okay? I just give you a hint. You can get excited about hearing about the curse. Okay. All right. Now, to address this, we first apply the notion of tautology from Lecture 1. Now, remember there's a notion of tautology in Lecture 1, A or not A, or A implies A, and we talked about tautologies. It means they're true under all sentential assignments. We can import the notion of tautology into this lecture, and we're about to do that. This is a very common theme also. Everything is a common theme, I guess. All right? So let's talk about this. So let's consider these three things. Well, maybe just these two things. I guess I left out one of them. I left out the first one. Okay, notice that these become propositional formulas, meaning these become the stuff of Lecture 1. If we view V5 equal V2 and V3 equals V4, if we view them as letters, if we view them as letters, in other words, factor out the fact that we're talking about Lecture 2, I'm giving Lecture 2, we can force this to be part of Lecture 1, right? And if we do that, what do we get? We get something like A or not A, and the other one we get A implies A, right? If I were to treat these things as letters. And those are tautologies. So that's what I mean by a tautology in this context. Okay. So in other words, these two formulas that I started the first line with are in fact tautologies in this in the sense of this in the sense of Lecture 2, which goes back to Lecture 1. Okay, clear enough? Okay. So now I'm going to give you some axioms and rules. We have the following axioms. X equals X. You believe that, right? X equals y implies y equals x. X equals y and y equals z implies x equals z. And x, y, and z can be any variables at all. Okay? Those are the axioms. Another bunch of axioms are called the tautologies. All variable formulas that are tautologies. All of the ones that are tautologies. For example, those ones up on the first line. Okay? Those are the axioms. And modus ponens says that from alpha and alpha implies beta, we can derive beta. And you're familiar with modus ponens from the context of the first lecture. This is one of a zillion sets of axioms and rules that are very good for this situation. Okay, this is not the only way to do it. Okay, this is just a neat, particular neat way to do it. Challenge: prove that these axioms and rules generate exclusively valid variable formulas. In other words, everything you get is valid by means of these axioms and rules. And the second challenge is to prove that anything that's valid, any variable formula that's valid is derivable by this in the system, generating the system. Okay. Now, these are both in the these are both somewhere in the open interval between easy and major parts of a course, and they actually are quite a bit distant from each other along that spectrum. And I leave it to you to figure out which ones, what the story is here. Okay. All right. Now we're going to now graduate to something more sophisticated, and something actually that is used throughout computer science context. I mean, it has plenty of applications in various situations. It's called equational logic. It's still a tiny little part of full-blown predicate calculus. See, I told you this would be done in general steps, okay? And obviously we should feel impoverished because this stuff just has variables. Mathematics uses functions freely. You can't do much mathematics without some basic functions. So for example, plus and times on the integers, very common thing people work with. And so we definitely want more power than this variable formula logic we've been talking about. Okay, so now we're talking about some real vegetables here. Okay, not just a glass of water. Where's my he didn't bring any vegetables for me. I have to ask next time. Next time I'm going to get some. I want some meat. Actually, in the rest of lectures 3, 4, and 5, we're going to have some meat. Okay, all right, all right. So today we're going to have vegetables and then a lot of fun at the end. That's as I told you. All right. So equational logic. Variables like before. Now we introduce a thing called constant symbols. Now what is a constant symbol? Well, if you remember the special role of 0 in mathematics, 0 is like a constant symbol. You're not allowed to vary 0, so to speak, but you are allowed to vary x. Okay? We also have function symbols, and these are n-place function symbols. So for instance, addition and multiplication are examples of function symbols that are binary, that are two-ary. Addition and multiplication would be an example. We also have equality, our old friend that we used before, and no connectives. We're going to get rid of the connectives. Now this is a little step backward for us, okay? This is a little step backwards. Okay, no connectives. All right. But this is already very, very interesting and very useful and very powerful already, even without the connectives. Okay, now what do the terms look like? We have a thing called terms. So for instance, you might know them as algebraic expressions, like x times y plus x times z minus w or something like that, right? Okay, so here terms are obtained by combining the above. So here are many examples of terms, just v alone. C, remember I told you I like to get rid of the subscripts on, and use different letters. Those things above there are just the official letters. Nobody uses official letters. Okay? All right, so, except in a proof, you wouldn't use it. Proof is something complicated. In a theoretical proof, you would have, but otherwise you don't want to read it. So VC, f of v, f of c, f of w, f of d, d is another constant symbol, h of xc, so there's h, a binary, used as a binary function symbol, And here's a more complicated one. We use H, J, and K. You can see that, actually, I see a little bug here. That H was used as a one place and as a two place, which is a no-no usually. So I have to fix that a little bit. So that last H should be that's actually a typo. It should be G. That last H should be a G. All right. Anyways, these are the random stuff thrown out for to give you an example. So and you should always indicate that V, X, Y, Z, W are variables and that C, D, E are constants. This should always be indicated because there's a subtle difference between variable and constants you want to be careful about a little bit because one is allowed to vary, the other is not. Okay. So equation logic, important branch of logic involving term equations only without the connectives. But the power of equation logic comes from using proper axioms. Proper axioms. And I'll show you what I'm talking about. Typically, you only use some constant and function symbols. You only use some of them. You don't use all of them. And use infix notation for binary function symbols, like plus. Nobody writes plus of A comma B. You like to write A plus B. It's another little twist when you actually use this. So I want to talk about, just as an example, a particularly famous collection of what's called proper axioms in equational logic, called the abelian group axioms. X plus Y equals Y plus X. X plus, raise your hand if you're familiar with an abelian group. Okay, so this is like a high percentage of people. Okay, now you're going to become familiar if you're not already. Okay, so we have the following proper axioms. X plus Y equals Y plus X, so-called abelian. Abel got so famous, they call it abelian groups, and he got so famous that people have started to not capitalize his name anymore. That's really a compliment. It's so famous you don't even capitalize his name. That's over the top. All right. Okay, so X plus Y equals Y plus X. X plus the associative law, the commutative law, the associative law, the identity law, X plus 0 is X, and the additive inverse law, X plus minus X is 0. Okay? Now, an abelian group is just a model of the above proper axioms. So we can view an abelian group as something, but nothing more or less than a model in the sense of logic of these particular axioms. Okay? And which I repeat up there. Now, in equational logic, more explicitly, a model of the proper axioms is a quadruple, D, comma, 0, comma, plus, comma, minus, where D is a non-empty set, 0 is in D, plus is some mapping from D squared into D, minus is a mapping from D into D, such that the proper axioms are true in the structure D, 0, plus, and minus, i.e. they're true in all assignments of elements of D to the variables. In this way, the models of these proper axioms are the abelian groups. Now, if I were just in lecture 1, I couldn't treat abelian groups with any seriousness in the scope of lecture 1. But now I can, you see. I can treat it in the framework of equational logic. All right, now here's an example of something an exercise that would typically be given, in an undergraduate algebra course. I mean, maybe if not this exercise, any of a number of similar exercises and harder ones. You might be asked to show that minus X is X in every abelian group or something like that, a typical exercise. And so, for example, you might write something like this. You might write minus X plus minus X equals 0. And what is that from? That's from the last law on the top of the page. X plus minus X equals 0, right? It's from that law. Because you learned that in algebra you make replacements, right? You can substitute. For X, you can substitute minus X, right? I mean, you're familiar with this from undergraduate algebra. And then, of course, I can add X to both sides on the left. I can add X on the left to both sides, right? So I get X plus that equals X plus 0. And that's X by the other law up there, X plus 0 equals X. And then, of course, I can rewrite x plus minus x plus double minus x as x plus minus x plus double minus x using the associative law, which is number 2 on the top of the page, right? And then I can collapse x plus minus x to 0. And then I can collapse that to minus minus x, except that last collapse comes from commutative law plus x plus 0 is x, right? The last collapse. 0 plus p equals p, right? I mean, I can get that from p plus 0 is p, and the commutative law. And then finally, I have a chain of implications, right? I start with the first one. Finally, I just get minus minus x is x. Oh, I see how I got that. Yeah, from number 2 and 3, from line 2 and 3. I get both x and double minus x is the same as that first term. See that first complicated term in the second and third line? The first one comes out x, and the second time it comes out minus minus x. So therefore it comes out that way. Now, if 2 students were to hand in why do you get minus minus x equals x, there's no chance at all they would wind up writing exactly the same thing. They'd do it slightly differently. Some of them would do it wrong. Some of them would do it hopefully right, and it'd all be, there's so many different ways you could do this, right? You can make this more complicated than this. Probably you might be able to make it a little simpler, Okay, so there's nothing unique about any of this, okay? But this is kind of like a proof, isn't it? Especially if you cite where things came from, from the thing. Okay. So I repeated all that. So now here are some theoretically convenient. I didn't say practically convenient. That's a whole other subject. Logic engineering is now a subject. In other words, trying to make proof systems neat so you can use them interactively with computers. That's a whole subject, which I will only maybe slightly touch on, in the 5th lecture when we're eating dessert. Okay. All right, now, here are some convenient axioms and rules for equational logic using the proper axiom set K. So a typical proper axiom set K is this thing on the first line here in small print. Okay, axioms, you can just write down any element of K. You can write down also x equals x, where x is any variable, and we have 2 sophisticated rules. The first one is from s equals t and p equals q, from 2 equations, I can derive a modified equation p prime equals q prime, resulting from replacing one or more occurrences of s by t. In other words, if I have an equation p equals q that I've already proved, and I also have on the side another equation, s equals t, then I can replace all the s's that I can replace any of the s's that I see by t in the equation p equals q. I can replace s's by t's. Where s and t, these are compound terms. These may be big compound terms. Okay, and the final rule is the substitution rule. If I have an equation s equals t, then I can replace any variables by any terms as long as I replace the same term with the same variables. So you saw we do that before. So for example, x plus 0 equals x. From there I can go to, say, minus x quantity. Quantity minus x plus 0 equals minus x, right? Because I replace x by minus x. But you can make multiple substitutions. In other words, we can have several variables being substituted, as long as you substitute the same term for the same variable. All right, here's the challenge. Show that these axioms and rules support the above proof. Well, that's a little bit vague, but the idea is to recast this proof, so to speak, so that it's covered by these axioms and rules. That's not that easy. It's not that straightforward, okay? It's not the major part of the course. But you'll learn something from that, okay? And now we have the completeness theorem for equational logic, which, now, what do I mean by that? Well, this set of proper axioms, K, proves s equals t just means s equals t can be derived from K according to the above axioms and rules of inference. And we say that K logically implies s equals t if and only if s equals t is true in every model in which all equations in K are true. Now remember, true in a model means true under all variable signs. And the challenge is first show that if K proves S equals T, then K logically implies S equals T. That's called soundness, actually. And that says that the system is at least reasonable. And then the bigger challenge is to show that if K logically implies S equals T, then K proves S equals T. This means that K captures everything you want it to capture. Right? In other words, anything that's correct is proved. That's what the second challenge says. And the first challenge says that anything that's proved is correct. Okay, you can chew on that. All right? Have fun with that. Now we're going to graduate, take a pretty big step, but it's all set up for us, so it's not going to be surprising. We've discussed variable formula logic where we only had variables, equality, and connectives, and no constant or function symbols. Remember that running out of water now, but that was the water, right? And then we had some vegetables called equational logic, where we had only variables, equality, constant symbols, and function symbols, and we had no connectives. Okay. Now we're going to combine both and also add another little item called relation symbols, which is no big deal. It's not as big a deal as function symbols are. Okay. So now let's summarize what we have. We're going to have in quantifier-free logic, we're going to have variables, we're going to have constant symbols, we're going to have equality, we're going to have function symbols, we're going to have relation symbols. So a typical, and we're going to have our usual 5 connectives that we already had in the first lecture. And we're going to have terms just like in equational logic, and the terms, of course, as in equational logic, would just involve 1, 2, and 4. Now, a typical relation symbol that occurs in elementary school math is less than. Is a typical relation symbol. So one thing is less than another becomes a statement. So that's how you position that idea, less than. It's a relation. Okay, so the atomic formulas of QFL are of 2 forms. First of all, S equals T, where S and T are terms. Secondly, RNM of T1 through Tn, where T1 and through Tn are terms. Okay, these are the statements. These are the assertions. You can say that 2 things are equal, or you can say that some particular relation holds of a bunch of items. And just to give you an example of what you can write, an example of a formula in quantifier-free logic, or a QFL formula, we have the following. F of xy equals g of xy, h of xc. Okay, those are 2 terms being equal. Implies not r of, so r is a relation of f of z, of 3 things, f of z, c, d, and g of w, x, w, and s of e, comma, f of c, c, right parenthesis around the whole thing. Okay? So there's nothing special about that, just a bunch of junk I put together, to illustrate connectives, terms, and relations, that's all. Okay? So you can see how complicated this can get. So you need some serious theory to be able to do anything. Okay, now the models take the form of a non-empty set D with objects Dn, functions, actual functions Fnm, and actual relations Rnm, where D is a non-empty set called the domain. Cn is interpreted by the element dn of D. Fnm is interpreted by the function little fnm from D to the n into D. And Rnm is interpreted by the relation little rnm contained in Dn. In particular applications, only certain constant function relation symbols are actually used. Okay, so this is actually the notion of model that's even used in full-blown predicate calculus, which is the full-blown big ticket item that we'll come to later. Okay, so the notion of model, that's a sophisticated notion. Fully sophisticated. All right, now in equational logic, we also have tautologies, and by treating the atomic formulas now as letters. And remember, we have a lot more atomic formulas because we now have function symbols and constants. QFL have a lot more atomic formulas than EL, yes. We retain the crucial feature of equational logic, treating proper axioms. So as in equational logic, these are interpreted universally. Okay. All right, an example of proper axioms in quantifier-free logic, the ordered abelian group axioms. The ordered abelian group axioms play an important role in math. They're models of these proper axioms using the symbols 0, plus, minus, and less than, where less than is a two-area relation symbol. So we have the familiar abelian group axioms in the first line. We have the axioms for linear ordering, the second one, that less than is a strict linear ordering. And the third one, we have the, I forget, I'm trying to remember the name for it. We have the axiom x less than y implies x plus z is less than y plus z. That's the really important axiom. That really makes this interesting. All right. The models of this set of axioms, proper axioms, are called the ordered abelian group axioms. Or just, excuse me, the models of this set of proper axioms, i.e. the ordered abelian group axioms, are just the ordered abelian groups. Just the ordered abelian groups. Okay. And you could not really neatly represent this without having a binary relation symbol. If you just had, and you also need connectives. So notice that this is not like the abelian group axioms where you didn't need connectives and you didn't need any relation symbols. This needs both relation symbols, in this case less than, and connectives. Notice I have, I'm using and, or, and I'm using implies, right? You see? So you really do need more and more power to be able to handle mathematical situations. Okay, so here's a sample proof from the ordered abelian group axioms, and I don't want to dwell on this too much because I don't have a lot of time, but this is straightforward. So you could be given the exercise x less than y implies minus y less than minus x. Okay, as an exercise. And you can do it by a chain of implications. If x is less than y, then you get this by adding minus y to both sides. Then given that consequent on the second line, you can get this by collapsing y plus minus y to 0, right, by the inverse law. And then you can, with that, you can add minus x to both sides. And then and that will be less than 0 plus minus x. Yeah, by adding minus x to both sides of the inequality in the third line. In the third line, you add minus x to both sides of the inequality. Then you can collapse. The x minus y plus minus x can be collapsed to minus y using associativity and commutativity, both. And then 0 plus minus x collapses to minus x by the identity. And now we have a chain of implications, right? X less than y implies this, implies this, implies this. We have a chain, so x less than y implies minus y less than minus x. Perfectly good homework hand in algebra, right? Okay. Now, somebody else might do it a little differently, right? There's nothing unique about this. Okay, now in general, this what is a proof in quantifier-free logic? Can we, again, can we handle proofs? Well, theoretically, yes, as follows. So I just rewrote the proof. Okay, axioms, all the elements of K, x equals x, two sophisticated additional axioms. The first one is x equals y and alpha implies alpha prime, where alpha prime is the result of placing one or more occurrences of the variable x by the variable y in the atomic formula alpha. So I have an atomic formula alpha. I don't need a more complicated formula. Atomic formula alpha. I can do surgery on it by replacing x's by y's, and maybe only some of the x's by y's. You get to choose which ones. Okay, and then alt tautologies, and then two rules. Substitution, which says that I can replace variables by terms as long as I replace the same variables by the same terms. And the second rule is modus ponens, that I can, that's from the first lecture, that if I have alpha and alpha implies beta, I can derive beta. Challenge, show that these axioms and rules support the above proof. Okay, and that's a little tricky, but you can, in other words, you can recast this proof, in this framework. It will be longer. You'll have to do more. Have more steps, because little steps are missing from that, thing. Okay. And now we also have the completeness of quantifier-free logic. I repeated the same system. Now K proves alpha if and only if alpha can be derived from K according to the above axioms and rules of inference. K logically implies alpha if and only if alpha is true in every model in which all formulas in K are true. This is the same definition of logically implies and proves that we used earlier in the lecture for equational logic. Same idea. And we have the same challenges. Show that if K proves alpha, then K logically implies alpha. That means that all the things that we prove are good. And the other challenge is if K logically implies alpha, then K proves alpha. This means anything good is proved. Okay. So it's so-called completeness. And this is the dream in logic, to be able to completely capture and show that everything good is proved. This is and everything proved is good. This is sort of like, been a preoccupation for a long time. Okay. However, sometimes you can't do this, and that's, as I said, comes up later. And there are obstacles to doing this in certain situations. Okay. Now I'm going to briefly go to full predicate calculus and then do some fun with it. Okay, so here we have variable formula logic was the first water, equational logic was some vegetables, quantifier-free logic was some serious vegetables. Okay, whole plate full of variety of vegetables. And now we want to go further and add quantifiers. So we're just going to add for all and there exists. And this is a complete list. 1 through 6 were already in quantifier-free logic, and now 7 is the additional items. For all and there exists. And mathematics cannot really be dealt with appropriately without that. So, for example, here's a formula. For every x, if not r of x, y, then there is a z such that f of x, f of z, h of y, c equals d, or whatever. Okay, so, and we use sets of axioms k and the same models as before in full predicate calculus. Same thing. And even if we have, however, here, even if we have no proper axioms, PC is rather subtle and powerful. So we call a formula valid just in case it's true in any structure under every variable assignment. And but more generally, if K is a set of proper axioms and alpha is a formula, we say K logically implies alpha if and only if alpha is true in every model in which all elements of K are true. Just the same setup we had before. But now we have quantifiers for all and there exists, and you have to incorporate that. What do you think for all means? It means for all. And what do you think the exist sign means? It means there exists. Just what you'd think. Okay. Now, I can give a nice axiomatization of PC in the spirit of the ones we saw for QFL, but this is, I think, a bit too much for one lecture. Besides, it's just more vegetables. It's a whole buffet table of vegetables, and I think that's not what I'm doing. I'm going to go shift into some fun, as I promised. All right. Everybody loves everybody. Somebody loves somebody. Everybody is loved by everybody. Somebody is loved by somebody. Everybody loves somebody. Somebody loves everybody. Everybody is loved by somebody. And somebody is loved by everybody. Now, this fits right into full-blown predicate calculus. Okay, we don't have function symbols, we don't have constant symbols, but we've got variables and we have quantifiers, and we have one relation symbol, binary relation symbol, L for love. Okay? L of xy means x loves y. So what does x loved by y mean? What does it mean to say that x is loved by y? It means L of yx, right? So now you can think about this carefully. You can translate the English into the symbols, the English into the predicate calculus like this. Everybody loves everybody. For every x and for every y, L of xy, and so forth. And think it through. Now, you have to be careful. Somebody loves everybody. Somebody loves somebody. That's great. Everybody is loved by everybody. Which one was I worried about? I'm worried about 5, 6, 7, 8. Not worried. I just want to point out something to you. In 5, we have what's called a change of quantifiers, alternation of quantifiers, or quantifier alternation. Everybody loves somebody. For every x, there is a y, L of xy. And then also in 6, we have it quite different. Somebody loves everybody. There is an x for all y, L of xy. And you should understand these are wildly different statements. Okay? And then we have everybody's loved by somebody, somebody's loved by everybody. Now the models are these systems D comma R, where D is a non-empty set and R is a binary relation on D. And the quantifiers range over D, and L is interpreted as R. Those are the models. Now there is a preferred model, namely the collection of all living people at the moment, and the love relationship. Of course, that's it's a complicated graph. It's a directed graph. For those of you who know about that, it's a directed graph. Or the like relation, which is a little bit different, right? But we're talking about the love rate. Okay, so this is a big deal. But in general, in theory, it's just D comma R. Okay, so I have some challenges for you. 1 and 3 have the same models, which is a way of saying that they're equivalent. 2 and 4 have the same models. Every model of 1 is a model of 1 through 8, and every model of any of 1 through 8 is a model of 2 and 4. Now let's have some more fun. How do we know that? How do we show that one of these does not logically imply a second? We give a model of the first that's not a model of the second. So, for example, a model of the second is B and C, and B loves B, and that's the only love relationship that B happens to love himself or herself, right? This is not a model of 1, since B does not love C in that model, right? B does not love C. All right, challenge. Show that 2, 4, 5, 6, 7, 8 altogether don't logically imply 1. In other words, give a model of all of 2, 4, 5, 6, 7, 8 that doesn't have 1. And also challenge, show that 2 does not logically imply the disjunction of 1, 3, 5, 6, 7, 8. In other words, give a model of 2 that doesn't, in which that disjunction fails. Now we're going to have yet more fun. The last, second to last slide. Determine which subsets of 1 through 8 logically imply which entries in 1 through 8. Okay, we're starting to get to some serious challenges here. Determine which subsets of 1 through 8 logically imply the disjunction of which subsets of 1 through 8. In other words, get a complete understanding of the logical relationships between all 8 of these statements. Okay? All right, there you are. So if you think that that's fun, here's a little more fun. Everybody loves everybody who loves everybody. Everybody loves everybody who loves somebody. Everybody loves somebody who loves everybody. And everybody loves somebody who loves somebody. Somebody loves everybody who loves everybody. Somebody loves everybody who loves somebody. Somebody loves somebody who loves everybody. And somebody loves somebody who loves somebody. Now, now this is a little trickier. This is trickier to formalize properly. So let's look at the first one. Everybody, that's for every x, loves not everybody, but loves everybody who has a certain property. It loves everybody who has the property that that person loves everybody. So if you look at this, you have to be very careful that number one formalizes properly number one up there. Before you leave the hall, the challenge is to work out all the logical relationships between these as well. This gets harder. Okay, and so forth. So it's already a little tricky for you to see that, in fact, I've actually written this down properly. Okay, that's already interesting. Okay, and now, of course, the challenge is which of these logically imply which of these, and determine which sets of these logically imply which of these, and finally, the biggest one of all, determine which sets of these logically imply which disjunctions of sets of these. Okay, with that, I conclude. Thanks very much.